Let's be honest, you've probably used the words mass and weight like they're the same thing. Hey, we all do it. But what if I told you that in the world of physics, they are not just different, they are completely different ideas? Well, today, we are going to settle this physics showdown once and for all.
So, let's kick things off with a little puzzle. You step on your bathroom scale, you look down, and it says 70 kilograms. Now, is that your mass, or is it your weight? Really think about it for a second. The answer might actually surprise you, and it gets right to the heart of what we're talking about today. We'll come back to this mystery at the very end, I promise.
All right, before we can properly get into what weight is, we first need to understand the category it belongs to. And at its very core, weight is a type of force. So, what in the world is a force?
In physics, a force is really just a simple idea. It's a push or a pull. That's it. Every time you push a shopping cart, pull open a door, or even when you're just sitting in your chair, yep, that's a force at play. Forces are what make things move, stop moving, or change direction. They're everywhere.
Okay, but here's where things get a little more interesting. You see, not all forces are created equal. Some forces only work when objects are actually touching, but others can act over a distance, almost like magic, without any physical contact at all.
Let's break this down. Over on the left, we've got contact forces. Think about the air physically pushing against that cyclist. We call that air resistance. The air has to touch the cyclist for the force to happen. Now look over to the right at non-contact forces. See how gravity is pulling that diver down? Nothing's touching him, right? It's a force that's working across space. And that is the category we're focused on today. So just to sum that up real quick, contact forces need to touch. Things like friction. Non-contact forces are the invisible ones, like how two magnets can push or pull on each other. And the most famous non-contact force of them all? You guessed it, the gravitational force. And that is the absolute key to understanding weight.
Okay, now that we've got a handle on what forces are, we have the tools we need. It is time for the main event, the showdown you've been waiting for, mass versus weight. Let's finally separate these two for good.
First up, in this corner, we have mass. Mass is simply a measure of how much stuff, or as scientists say, matter, an object is made of. It's literally the total amount of atoms and molecules inside you. And the standard unit we use to measure it is the kilogram, or kg. Now this is probably the most important thing to remember about mass. Your mass is constant. It never ever changes. It doesn't matter if you're on Earth, on the moon, or floating in the middle of deep space. The amount of stuff you're made of stays the same, so your mass is always the same.
And now for the challenger, weight. Weight is not the amount of stuff in you. No, weight is the force of gravity pulling on all that stuff. And since it's a force, its official scientific unit is the Newton, which we write with a capital N. Yep, named after the guy who figured it all out, Sir Isaac Newton.
This table really puts it all side by side. Let's look at that type row. Mass is a scalar, which is just a fancy science word for a number, like 70 kilograms. Easy. But weight is a vector. That means it's not just a number, it also has a direction. Your weight is a force that's always pulling you down, towards the center of the planet. And now for the knockout punch, the last row. Mass is constant everywhere. But your weight? Oh yeah, that definitely changes depending on where you are.
Okay, so if your weight can change, the next big question is why? I mean, what is it about going to a different place that changes the force of gravity pulling on you?
Well, the answer is something called a gravitational field. Think of it like this. Every huge object, like a planet or a moon, creates this invisible field of influence all around it. When you step into that field, it grabs onto your mass and exerts a pull. That pull is what we feel as our weight.
This elephant is the perfect example. Check it out. Its mass, the amount of elephant stuff, is a huge 10,000 kilograms, and that doesn't change. But its weight, totally different story. On Earth, gravity yanks it down with a force of 100,000 newtons. But on the moon, where gravity is much weaker, the pull is only 16,000 newtons. It's the exact same elephant, but it weighs more than 6 times less on the moon. And you know what?
There is a beautiful, simple little formula that connects all of this. Weight equals mass times gravitational field strength, or, as we physicists like to say, W equals mg. This tiny equation is seriously one of the most important in all of physics. So let's quickly break that down. W stands for weight, and we measure that in newtons. M is for mass, which we measure in kilograms, and that little g represents the gravitational field strength. It tells you how strong the pull is in a certain location. Its unit is newtons per kilogram.
Now right here on the surface of Earth, the value for g is approximately 10 newtons per kilogram. So what does that mean? It means for every single kilogram of mass an object has, the Earth pulls down on it with about 10 newtons of force. For your O-level exams, this is the magic number you're going to use.
Okay, it's time to bring this all home. Let's put all the pieces together and deliver the final verdict in the great case of mass versus weight. This map ties it all together beautifully. See? You start at the top with mass, that's the amount of matter you have. You follow that arrow, and when your mass is in a gravitational field, it creates weight, which is a force. And the bridge connecting them is that awesome formula, W equals mg. See how it all just connects? So, what about that bathroom scale from the beginning? Here's the big secret. Your scale is really a force meter. It's measuring the downward force of your weight. But then it does a clever little trick. It takes your weight, divides it by g, which is about 10, and then it displays the answer. So here's the final reveal. Your scale measures your weight, but it tells you your mass. Pretty clever, huh?
All right, to finish up, I'll leave you with a final challenge. On the massive planet Jupiter, the gravitational field strength G is a whopping 25 newtons per kilogram. So, if your mass is 70 kilograms, what would your weight be on Jupiter? Grab a calculator, use the formula, and see just how heavy you'd feel. That's the power of physics right there. Thanks for tuning in to This Explainer.